Hi everyone, my name is Yerin Kim from Seoul National University. Today I am pleased to present our paper, Bi-ICE, an inner interpretability framework for image classification via bidirectional interactions between concept and input embeddings. This research was conducted in collaboration with Jinyoung Hong, Keuni Park, and Sang-Yu Han, alongside with Nojum Kwak and Theodore P. Pavlik. Current explainable AI methods typically highlight which pixels influence a prediction or identify high-level concepts associated with a class. While these are useful for detecting bias or providing user-facing explanations, they leave significant practical problems unsolved. They don't tell us why a model fails internally, which representations are being confused, or how reasoning actually forms during training. To truly debug and improve AI, we must make the internal reasoning process observable. This brings us to inner interpretability. Unlike existing explanation methods, inner interpretability seeks to explain the actual mechanisms. What representation form inside the model? How do internal components interact? Or how does reasoning emerge before prediction? In other words, instead of explaining outputs, we try to understand internal mechanisms that produce those outputs. So interpretability moves from explaining decisions to explaining reasoning itself. Inner interpretability aims to uncover the internal mechanisms that produce model behavior. However, mechanisms does not exist at only one explanatory level, but they span multiple levels. To see this intuitively, consider a simple calculator computing 107 plus 14, giving 121. We can explain this in several ways. At the highest level, we simply say the calculator performs addition. That describes what problem is being solved. At another level, we explain how addition works. Digits are added column by column, and when sums exist 10, we carry over. That describes the algorithm being used. And at the lowest level, we explain how this is physically realized using electronic circuits and silicon chips performing operations. Each explanation is correct, but none alone fully explains the system. If we only look at circuits, we miss the algorithm. If we only describe the algorithm, we ignore how it is implemented. The same issue appears in neural networks. Many interpretability methods only inspect neurons or attention maps, which tells us where computations occur, but not why or how reasoning unfolds. So to truly understand reasoning inside the models, we need to connect all these levels: what the system computes, how reasoning occurs, and where it is implemented. This is why multi-level analysis becomes necessary for inner interpretability. Now that we understand why multi-level analysis is needed, the next question is how to apply this framework to image classification. Traditionally, image classification is formulated as a direct mapping from image features to labels. While this works well for performance, the reasoning process inside the network remains opaque. We don't know how internal representations combine to produce those decisions. So in our work, instead of starting from architecture design, we first reformulate the classification problem itself in a way aligned with multi-level analysis, and then evaluate interpretability at each level. After defining classification as concept-based reasoning, the next question is how to realize this reasoning in neural networks. This is where our Bi-ICE modules comes in. Bi-ICE acts as a hub between image embeddings produced by backbone models and a set of learnable concept representations. First, image features activate candidate concepts by binding concepts to relevant image regions. And then those activated concepts broadcast information back, refining image representations. Through this interaction, perceptions and concepts improve each other. Finally, predictions are made from embeddings that have already incorporated concept reasoning. So instead of a one-pass mapping from features to labels, prediction emerges after perception and concepts interact. Before discussing interpretability results, an important question is whether adding interpretability harms performance. To evaluate this, we tested Bi-ICE on standard image classification datasets, comparing backbone models with and without our module. Importantly, Bi-ICE is attached to pre-trained networks rather than replacing them, allowing us to check whether reasoning modules disrupt learned representations. The results showed that classification accuracy is maintained or slightly improved. This means that enabling concept-based reasoning does not degrade performance. So interpretability here is not a trade-off with accuracy. Instead, we gain transparency while preserving predictive power. With the performance confirmed, we will now evaluate our framework through the 3 levels of analysis: computational, algorithmic, and implementation. At the computational level, the question is what the problem is solving. In our framework, classification is defined as concept decomposition. To test this, we analyze how concept activations contribute to final class predictions. We observe that predictions can be decomposed into contributions from learned concepts, meaning that the model bases its decisions on concept-level evidence rather than the opaque features. Furthermore, many learned concepts align with human understandable attributes, showing that the model organizes reasoning around interpretable structures. So at the computational level, classification is indeed achieved through concept reasoning consistent with our formulation. At the algorithmic level, the question becomes how the model processes information to produce decisions. In our framework, reasoning happens through interactions between image embeddings and concept representations. We observe that concept representations become more distinct as training progresses, indicating that the model organizes information into stable conceptual structures. Additionally, concept activations stabilize over time, showing that reasoning becomes more consistent before predictions are made. So rather than producing decisions in a single opaque step, we can observe reasoning dynamics forming and stabilizing within the model. This validates that our model implements interpretable reasoning at the algorithmic level. Finally, at the implementation level, we examine how reasoning is realized within the network. Here, we visualize how concepts contribute to predictions across image regions. Each concept shows activation patterns corresponding to meaningful parts or attributes in the image. For example, certain concepts activate around the wings, legs, or body regions in bird images, showing that the model relies on interpretable visual evidence. This allows us to see not only which concepts are activated, but also where they are grounded in the input. So reasoning becomes observable both conceptually and spatially, computing interpretability across all levels. To summarize, our work first proposed a conceptual framework to reformulate image classification in a way aligned with multi-level analysis. We then introduced the Bi-ICE module to realize concept-based reasoning in neural networks. Finally, we evaluate interpretability across computational, algorithmic, and implementation levels. And this enables predictions grounded in human understandable concepts and makes decisions formation transparent and allows us to know the reasoning dynamics observable. Overall, our work shifts interpretability from explaining predictions after they made to understanding how reasoning forms inside models. Thank you for listening.